We are talking about 8.4, and it's domain and vertical asymptotes. So we're going to break this up, and then there's going to be another lesson on holes and horizontal asymptotes. So we're breaking this up into sections. A function in the form r of x equals p of x over q of x. So it's a rational function. So instead of being a rational expression, we're now going to have it equal as a function. And it says q of x can't be 0. That's because our denominator can't be 0. This creates those domain restrictions that we've been talking about. That's supposed to say domain restrictions. That creates those domain restrictions. P and Q are going to be polynomials. And so we're not doing anything new. We are going to be factoring, reducing, cleaning up, but we're also going to focus on what the graphs would look like. So we know if it's one term, it's a monomial, 2 is a binomial, 3 is a trinomial, and 4 is a polynomial. So 4 or more. Examples of rational functions. These are all rational expressions, but the minute I set it equal to f of x or y, it has now become a function. Okay, so a rational function follows all the rules of a polynomial. The polynomial can't have any variable exponents. It can't have any negative exponents, can't have a fractional exponent, can't have a root. All of those can't be on the variable. So it says, which of the following are rational functions? If they are not rational functions, explain why. So let's take a look at this. Is this a rational function? Well, the numerator has a monomial and the denominator has a binomial. Everything looks good. So yes, it is a rational function. All right, let's look at B. Is this a rational function? Answer is no. It's right here. What is the power of 1/2 the same as? Same as the root. So whether I wrote it like this or I wrote it with the power of 1/2, it is not rational. And it's not rational because it has a fractional exponent. Not rational has a fraction or fractional exponent, or it's not rational because it would be a root. All right, so take a peek and look at example C and D. What do you think about C? Rational or not? Rational. But look at your power. You can't have a fractional power, you can't have a root, but you can't have a variable as your power. Now, if I had x to the 5th, would be good. So this is not rational because there's a variable in the exponent. Variable in exponent. So it's all these little things we're looking for. What about D? That one's rational. Power of 1, we're good. All right, what about E? E is prefactored. We could FOIL that out, right? And we would have the quadratic, but this is rational. What about F? Now, this is one that didn't come up. Again, it would have come up in sort of the study of polynomials. This is not rational. You can't have a variable in an absolute value. So not rational. No variables in absolute value. Well, I guess I'm saying you can't have it. That's why it's not rational. So you can have an absolute value of a number, but you can't have a variable in there. Okay, so I just want to remind you, what makes something not rational, not a polynomial? A fractional exponent or a root, absolute value, or a power that's a variable. All those things we're not going to use. So when you see these problems, you're not going to see any of those ideas. Now it says use the functions from example 1 that were defined to calculate the domain for each. So let me put this back together so you can see it. You might just flip it back to the front. It says calculate and find the domain for each. So let's just flip back to the front. So I'm going to say C front. And I'm just going to do that on the front. That way we don't have to flip back and forth. So let's find the domain. Look at example A. What's the domain? Well, I can't divide by 0. Agreed? So the domain means that my denominator cannot equal 0. So can't equal 0. Add 7, right? Divide by 2. So my domain restriction for this would be x cannot equal 7 halves. Now, it asks for the domain. This is the domain restriction. The domain would be all real numbers except 7 halves. Do you get the idea there? Okay. Domain restriction is a little bit easier because we don't have to say everything else. All right, so we don't have to do B or C. What about D? What is the domain of D, or domain restriction? My denominator can't equal 0. So what would make my denominator equal 0? If x was 0. So my domain restriction, x can't be 0. That means it could be any real except 0. So how would I show that in interval notation? You would say it can be negative infinity to 0, don't include it, and then union 0 to infinity. So do you see if I was graphing a number line? This is what it would look like. It'd be like an open circle, and then I would shade everything above and everything below. Are you translating? So this is what it can be. Oh, sorry. This is what it can be. Anything below or anything above, not including 0, this is what it can't be. Okay. Domain of example E. Well, this is the quick one, right? What would make that 0? If x was negative 3, what would make this 0? Well, if you're not sure, set it off to the side. Wouldn't it be a negative 2/3? Because you have to subtract. So that might be worth writing it out. You're subtracting 2 and dividing by 3. All right, we are going to be using our domain restrictions to help us to understand what the graphs do. Okay, so we're not solving anything. We're just looking at the pieces here. All right, now find the domain of each rational function. Okay, so this is a quadratic trinomial divided by another quadratic trinomial. In order to find the domain, what do I need to focus on? Factoring, but what part? The top, the bottom, or both? Just the bottom. Okay, so I'm going to focus on factoring the bottom. You know, if there's a GCF, take it out. Pretty simple factoring because A is 1. So what am I using? Positive 4, positive 5? Okay, so we don't want this to equal 0. So we want to say x cannot equal negative 4 or negative 5. These are my domain restrictions. It would take a little more effort to show the domain because you'd have a couple chunks for your interval notation. So domain restriction is good with me. All right, next one. How does the denominator factor? Because that's what we don't want to equal 0. Positive 3, negative 1. Do we agree? Okay, what would make the first piece 0? My domain restriction is that x cannot be negative 3 or 1. Now, I could factor the top, maybe cancel something out, but they're not asking me to simplify. They're only asking for the domain restriction. So I'm not going to do the extra work, but we're going to talk about that now. All right, something that I know you probably haven't heard of, unless I mention it in here, I think once or twice, is this word asymptote. So an asymptote is a line that a curve approaches but never reaches. So see how this line is going, or this curve is going up, 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 and this curve is going down, down, down. There is an asymptote between here. It's like a boundary line, and the line is never going to, the curve will never touch it, and it will never cross it. And you see that there's another one right here? So you have this curve that's going, but it's never going to touch. It's going to get closer and closer to 0, but never touch 0. This is going to get closer and closer. So as x gets closer to 3, the y increases. As x gets closer to 3 from the left, the y decreases. So that's what an asymptote looks like. All right, so let's write the definition. It is a line that a curve approaches but never reaches. A line that a curve approaches. It's like a boundary line or a fence. Yes. but never reaches. So we can investigate these on a graphing calculator, but let's talk about it algebraically and with the graph. First things first, we're only focusing today on the vertical asymptotes, okay? So if you look at this, look at the denominator. What would be the domain restriction here? X cannot equal 3. And do you notice that that is an asymptote? What's the domain restriction on this one? X cannot equal -4. And guess where there's an asymptote? Right there at x equals -4. Remember, you define your vertical lines as x equals because it cuts through the x-axis at 3 at -4. Now this graph's sort of popping all over the place, but do you see that it's approaching but sort of stuck here and here? So this line would be at x equals -2, and this asymptote would be at x equals 3. All right, so let's talk about the denominator. Factor this. It'd be x plus 3 over what? A -3 and a +2. A lot of people want to do like -6 and 1, but it wouldn't add up right. Okay, do you notice my domain restriction? X cannot be +3, x cannot be -2. So can you draw any conclusions about vertical asymptotes and domain restrictions? Whatever your domain restriction is creates a vertical asymptote. Now there is a caveat with that, okay? If you look at this, nothing cancels or reduces in these. Like you can't simplify these fractions. So these domain restrictions are creating these asymptotes, but if a domain restriction cancels out, we'll talk later that creates a hole. So there's that. So let's write down what we just sort of made a hypothesis about. Vertical asymptotes occur where there's domain restrictions, occur at the values of the domain restrictions. Okay, vertical asymptotes occur at the values of the domain restrictions, and the domain restrictions come from setting the denominator not equal to 0. Remember, domain restrictions come from the full denominator before you cancel. So we are going to put our hypothesis to the guess or to the test and look at these next two problems. So first one, I am not worried about the numerator. I'm worried about the denominator. So factor that denominator for me. Notice these aren't real tough factoring. X what? -2 and +1. So what would be my domain restrictions? X cannot be 2 or -1. So what is the guess for my asymptotes? And I'm going to use the term VA for vertical asymptotes a lot. My guess would be there's going to be one at x equals 2 and one at x equals. Okay, I need you to see the difference here. If I asked you to, if I gave you this and I said, solve this quadratic, you would set it equal to 0 and say x is 2, x is -1. That's solving it. Find x when y is 0. Sorry, yeah. I'm asking you to use this for the domain restriction. My domain restriction says that x can't be 2 and x can't be -1. I need you to understand that your vertical asymptote is a line. And remember, vertical lines have an undefined slope. So that's why I'm writing it x equals 2. I am telling you there is a vertical line at x equals 2 that the graph will approach but never touch. So I want to make sure we're clear what I'm saying. It can't equal and why it does equal. Okay, look at the next piece. Now, if I was factoring, how would this denominator factor? Go ahead, take a second and do it. X what? +3. And x plus 3 again. So this is x and then x plus 3 squared, but I'm going to leave it like that. So what are my domain restrictions? What can't x be? 0 and Just negative 3. So not plus or minus 3, just the negative 3, right? Okay. So, well, more than the 0 cancels.
Then one of the x plus 3.
Okay, so we're going to talk about that. Now, based on our theory, we would think that we have vertical asymptotes at x equals 0 and x equals negative 3. Now, you brought up a good point. If we were simplifying this, if I said, hey, I need you guys to simplify this, just like we've been doing, you would come in here and you would say, the x's cancel and this cancels, and what's left? And don't you dare tell me x plus 3. What's left? 1 over. So y equals 1 over x plus 3. Okay, so I want you to remember that, yeah, some things cancel, but we're assuming if it's a domain restriction, it's a vertical asymptote. Okay, flip it over. These are the same two problems we just had. So if you look at this, it says, look below to check the graph of each function and see if your guesses from part C are correct. Are my guesses correct? Okay, well, look at this function. Sketch in that vertical asymptote. What would that vertical line be defined as? X equals 2. And if we went back to what we did on the front page, we had this factored as x minus 2, x plus 1, right? But we said, yep, there's a domain restriction that x cannot equal 2 or negative 1. So we assumed that there was a vertical asymptote at 2 and at negative 1. Is that true?
No.
Okay, now look at your function. If we rewrote it and we simplified it, what happens here? Just like the other one, don't the x plus 1s cancel? And that leaves me with y equals a simplified function of 1 over x minus 2. All right, any thoughts here? What's pretty simple? Like, why don't I have an asymptote at x equals negative 1 like we thought we would? Okay, so if it cancels out, it's not an asymptote. It's what's left in the denominator. So domain restrictions always come from the original denominator, but the asymptote comes from the simplified denominator. That gives me my vertical asymptote. Okay, so we talked about this one, and when we looked at it, we had it factored down, x plus 3, x plus 3. And as much as it's x plus 3 quantity squared, I like to write it out. So I'm going to see these x's cancel and these cancel. And my simplified version is y equals 1 over x plus 3. Where is my asymptote here? It's only at x equals what? I'm going to put VA so we get in the habit of vertical asymptote. It's at x equals negative 3. What was my domain restriction here? X could not be 0 or negative 3. So we assumed on the other side, we had a vertical asymptote at 0 and negative 3. 0 is still a domain restriction, but my vertical asymptote is based on what's left. So I only have a vertical asymptote from here. All right, so how do we find a vertical asymptote, guys? How do you find it? What do you need to do? Okay, well, first let's talk about factoring. To find a vertical asymptote, you're going to factor the both parts. Factor the numerator and denominator. So if you're only asking for a domain restriction, we only have to worry about the denominator. But if you're doing asymptotes, vertical asymptotes, we got to do both. So factor the numerator and denominator, cancel or reduce any common factors. Cancel any common factors. Okay? Then what? The remaining factors in the denominator. Remaining factors in the denominator give the vertical asymptote. So then the factors in the denominator give the vertical asymptotes. So how do I find that? I set them equal to 0. So set equal to 0. Okay, so hopefully that reminds you of this, because we are going to talk about other things too. This seems a little bit blurry. Maybe it's just me. All right, so before we move on, let's just practice real quick. I'm not looking at a graph. It says identify all the vertical asymptotes, but I'm going to put on here that we also want to be good about always giving the domain restriction. So first things first, I'm going to leave the numerator alone. Do you guys notice there's a GCF of x here? So I'm going to do this as 2 steps, but I'm just going to show it here. All right, so there's my numerator. My denominator, factor this out. X plus 4, x plus 1. This is my function f of x. Okay, does anything cancel here? Yes. So simplified function, make sure you put that 1 on top. On the bottom is x plus 1. What were my domain restrictions as I would always list them? What can't x be? Well, domain restrictions come from here. X can't be 0, -4, or what? -1. Those are my domain restrictions. Now, based on this, what are my vertical asymptotes? Well, what's left in the denominator? The 0 and what? So, and we write it as x equals. I can't stress this enough. Domain restrictions, I can just list after the x does not equal. But when you're doing vertical asymptotes, each one should have its own x equals, because you're defining separate vertical lines. Okay? All right, so look at the next one. First thing I'm going to do is take out the GCF in the top. So don't forget that basic GCF. And then the top's good. The bottom is going to have a GCF of x, and then let's factor that down. Again, more basic factoring, okay, but you should be able to factor all types of problems. Do you have a -3 and a +1? So what does this simplify to? Yeah, the x's and the x minus 3 cancel. You might have something still left in the numerator, but this is 1 over x plus 1. What are your original domain restrictions? X cannot equal 0, 3, or -1. Got it? So this is, this is all part of my answer if I just said simplify this, but I'm asking for the vertical asymptotes. What's left in the denominator? X plus 1, so x equals -1. So we're going to talk about this tomorrow. If it cancels out, the 0 and the 3, they're going to create a hole in the graph. Literally an open circle that we just jump over. We have to figure out where that hole is. We just know it's at a 0 and a 3 on x. But whatever's not canceled out creates this vertical asymptote. So that's what we're looking for, but there is my work to get there.